All right, yesterday we finished up talking about geometric isomerism. We said that that's not absolute. We had two examples here where we couldn't assign R or S to either of the stereocenters because they aren't stereocenters, but we can identify them as cis or trans. I will tell you guys, though, I'm kind of picky about this. I'm going to write this down. Use R or S to avoid confusion if possible. We saw in the above example it was impossible to use R or S, so that's when we use cis or trans. But I'll show you guys a situation. So for example, let's consider the following. Cis, 1 bromo, 2 chloro, hexane. What will this look like? So I'll draw 2 cyclohexanes and we'll compare them. What does cis mean again? Same side. So I could have a bromine coming off that's a wedge, which means the chlorine coming off this position must be what? A wedge. Okay. Or I could have the bromine as a dash, and the chlorine would be what? A dash. What's the relationship between these? Are they the same? It looks like position 1, I switched it from a dash to a wedge, and same with position 2, so I flipped all my stereocenters. So what would the relationship between these be? Enantiomers. So if we think about this, cis does not clearly identify which enantiomer you have. However, if we use R or S designations at the beginning, then we would clearly be able to identify which of these two enantiomers we were talking about, right? So try to use R and S if possible. If not possible, then use cis or trans. Does that make sense? It's a little bit confusing. All right, so let's move on to alkenes. I know this is kind of out of order, and we're going to cover alkenes a little bit later on. But we've got some geometric isomerism with alkenes. So again, cis versus trans alkenes. For some of you, this will be a review, but let's try to name these. Which one is cis? The one on the left or the one on the right? The one on the right. Okay, so this one's cis. And the way I remember this is if you cut this in half, it's got identical substituents on the same side. However, over here, we've got them on opposite sides of that double bond, right? So this must be our trans isomer. What's the relationship between these two molecules? Are they enantiomers, diastereomers, constitutional isomers, identical? I would say you still have a methyl group coming off of carbon 2 and a methyl group coming off of carbon 3 for each of them. Diastereomers, right? Because they're not mirror images. They're not mirror images. Do these have the same physical properties or different? They're going to be very, very different. In fact, they'll have different melting points, different boiling points, and so on. So we have to be very, very careful with using cis versus trans for alkenes. But let's talk about kind of an odd example. Okay, what about if I have this alkene where I've got a fluorine, I've got a hydrogen, I've got a chlorine, and I've got a bromine. Is this cis or trans? Trick question, right? You can't identify cis or trans because we don't have identical substituents coming off the same face or opposite faces. So let me make a little note. This is neither cis or trans. All right, let's compare this to another alkene, though. All right, for this one, I'm going to have fluorine and bromine. Got chlorine and hydrogen. Is that cis or trans? It's neither, right? Okay, so we know we can't use cis or trans. All right, so I'll put that up here. Not cis or trans for either. All right, what's the relationship between these now? Are they identical? Are they enantiomers? Are they diastereomers, constitutional isomers? What do you guys think? Diastereomers, right? They are not mirror images. So these are diastereomers. However, we can't use cis or trans to differentiate the one on the left to the one on the right. So we actually have to come up with a new naming convention to be able to distinguish these. In cases where you don't have cis or trans, you have to name them differently. So I'll show you guys how you do that. And again, all I'm going to do is cut these with an imaginary line down the double bond. And what I want you to do is focus on this left-hand side, right? Which is a higher priority substituent, bromine or fluorine? Why bromine? Because it's heavier, right? Okay, so bromine, because it's heavier, is going to be position 1, and then fluorine is going to be position 2. All right, now the same thing on the right-hand side. What will be higher priority? Chlorine, okay. So I'd say 1 and then 2. So what I would do is I would say the highest priorities are on the same side. And this is referred to as a Z alkene. All right, we could do the same thing to the one on the right. So we know bromine's more important than fluorine, so we'll put that 1, fluorine 2. And then on the right, we've got chlorine as 1, hydrogen on 2. So for this one, it's a little bit different. The highest priorities are on opposite sides. And this is referred to as an E alkene. The naming conventions actually come from the German words meaning together or opposite. So I think it's Enttogen, means opposite, and I can't remember for Z. But I will show you guys the trick I used to remember this when I was in undergrad. I remembered it using a cheesy mnemonic, Z same side. Right? So have your cheesy French accent and be Z same side. Oh yeah, that's a Z alkene. E means opposite, right? So you can use that if you'd like, or you can ignore me and just remember it your own way. But you do want to differentiate the two diastereomers as either a Z alkene or an E alkene because they are unique and different from one another. Does that make sense? We'll come back to alkenes and naming alkenes later on this term, specifically the last chapter of the term, but I wanted to show you guys the stereochemistry designation for each of them. All right, now we get to get into some of the weird lab stuff. So purification or isolation of various stereoisomers is a big deal. All right. How can we purify two different diastereomers, meaning separate them from one another? It's a lot easier, right? Because we know diastereomers have different physical properties. So they have different physical properties, which means you can purify them by using things like distillation, because they've got different boiling points. You can separate them using chromatography. All chromatography is, for the most part, is separation by difference in polarity. So for example, you've got this stationary phase that your compound is forced to travel through. The more polar compound might travel more slowly than the less polar compound, and so you're able to separate them that way. You can separate them by recrystallization because they have different solubilities. In fact, they're just completely different from one another. So we'll write easy to separate due to different physical properties. All right, let's move on to enantiomers. All right, can we separate an enantiomer or a pair of enantiomers using distillation? No, they have the exact same physical properties, which kind of rules out distillation, standard chromatography, because they have the same polarity, right? And they have the same solubility, so you can't use crystallization. However, I will show you guys how it was first done. The first method actually did involve crystallization. And what happened was each enantiomer has its own shape. And the opposite enantiomer is the mirror image. So the analogy I like to use is, imagine a pair of shoes, right? A pair of shoes, they're mirror images of one another, so you could consider them enantiomers. So if all you had was a big pile of shoes and you dumped them in the room, you could say, all right, I'm going to sort the left-handed shoes from the right-handed shoes physically, right? This was actually how they first did it. They would crystallize it. They would get a pile of crystals underneath the microscope. They would pull out little itty-bitty tweezers and move the right-handed ones to one side, the left-handed ones to the other side, and it took forever. So how many of you have heard of Louis Pasteur? He was actually the first person to describe this unique characteristic and actually described what enantiomers are, and he did this with tartaric acid. And so, all right, requires physical tweezing. It's a pain in the butt, and I wouldn't recommend doing it. But it's something you could do. The next one that's more popular is using chiral resolving agents. And I'll show you guys how this one works down here. So if you've got a chiral resolving agent, you might have a pair of enantiomers. So for this one, I'm going to borrow it from the book. You've got an amine where one is a wedge and the other one is a dash. And these are mixed together, and you want to separate them out, but they have the exact same physical properties. So what you're going to do is you're going to react this with a chiral compound. Sorry, let me move this arrow down. And this is S-maleic acid. And the key with this is that it is a naturally occurring chiral compound. So you can get a bunch of different sugars or amino acids, things like that, that are naturally pure enantiomers, so they're exclusively R or exclusively S. And what do you think will happen if you react to an amine with this compound? What functional group do we have over here? Carboxylic acid. And an amine is a pretty good base, right? So all we're going to do is steal this proton, or this one can steal that exact same proton. It doesn't really matter anymore. So let me extend this arrow over, and we'll draw our two products that we get out. So up here we have NH3 plus, that's our conjugate acid. Down here, we've got it as a dash. And because it's a salt, it must have a corresponding anion, right? So the anion in this case has got to be the conjugate base. Oops, sorry, that should be a wedge. And then same thing down here. We've got our conjugate base. And now we've got this compound in the red box, that's a salt, and this compound in the green box, that's a salt. Do we agree on that? What's the relationship between the red box and the green box? What do you guys think? Let's think about it this way. Let's focus on the red box right now. Oh, I should change the pen color. What's the stereo center here? Is it going to be R or S? S, exactly. Which means the one below it will be what? R. Okay, so that's not too bad. Let's go over here. What's that stereo center going to be? S. So you can go through and double check. What about this one? S. It's the exact same. All right, so when we compare the red box to the green box, it looks like we've got two different stereoisomers, which means the relationship between these must be what if one of them was flipped and not both of them? Diastereomers, exactly. So during this whole reaction, it's a little bit weird to think about, but we've created a pair of diastereomers. That can be that can be separated. So for example, you might be able to crystallize one differently than the other now. All right, once you're done separating them, how can you get back to your original compound? All I would do is just deprotonate it using a weak base, right? So after you deprotonate it, then you would have your pure compound. So chiral resolution takes advantage of these naturally occurring chiral compounds. It forces your compound to form a set of diastereomers. You can separate those and then get back to your starting material later on using acid-base chemistry, for example. So it's a little bit weird, but it's commonly done. So crystallization, we said, is super duper tedious. Chiral resolving agents, yeah, they're kind of tedious, but they work really well. There's also one last one that's more modern, so I wanted to show you guys this one. This is chiral chromatography. So I said normal chromatography exploits difference in polarities to separate out molecules. There are other techniques though. So let me explain what's going on with this one. So chromatography utilizes non-covalent interactions with a stationary phase, meaning some sort of support that your compound's forced to go through to separate molecules. Oh. All right. And then the second part with chiral chromatography is the key part. If your stationary phase is chiral, then each enantiomer will flow through it at different rates. It's a little bit weird to think about, but if you've got a chiral stationary phase, that essentially has a handshake type interaction with the corresponding enantiomer that fits it. So those will dock and kind of hang on more tightly than the ones that are the opposite hand that can't lock in. And so you can actually separate your enantiomers using chiral chromatography. So if we look at all three of these possible options, number one we said is really not done because it's way too tedious. Number two is cheap and easy, but does require a little bit of legwork. Number three is pretty expensive, but doesn't require going through those intermediate steps. So really it boils down to how much money you have. If you're super duper wealthy, you will buy the chiral columns. If you're poor, you're going to do the chiral resolving agents. So each of them can be used, and they're commonly observed in a bunch of different organic chemistry labs. Yep. That's a good question. It really depends on the type of column that you buy and how good you are with your chromatography techniques. But I would argue chiral chromatography, given our current instrumentation, is pretty hard to beat. Yeah. All right, there's one last thing before we get started on our small group activity. And they kind of just throw this in last minute. I don't necessarily agree with the placement in the chapter. But it's Fischer projections. Fischer, or Emil Fischer, was the chemist who studied all of the early carbohydrates. And if you've seen carbohydrates, they're full of 1 million stereocenters. And it gets really complicated to draw out all of those stereocenters using bond line notation. So Fischer came up with a common shortcut that's still used today. For drawing stereocenters. All right, it's pretty easy. All horizontal lines are wedges. And then all vertical lines are dashes. But he doesn't show them with dashes or wedges. It's just assumed, right? So anytime you see horizontal, assume that it's a wedge. Anytime you see vertical, assume that it's a dash. So I'll show you an example of this. Let's say you've got this compound. We know we have a stereocenter, right? Because we've got 4 different substituents. And so he likes to show these as just a simple cross or a T. If you wanted to draw this using standard bond line notation, it would look a little funky, but here's what it would look like. You'd have your OH as a wedge. Your other hydrogen would be a wedge, so it looks kind of like a bow tie. Can you guys see that? And then the ethyl group coming up must be a dash, and then the ethyl group going down, methyl group going down must also be a dash. Does that make sense? So your backbone that's going vertically up and down is curved away from you. Everything else is sticking out towards you. All right, so let's assign stereochemistry to this now. Highest priority for that stereocenter. Oxygen, followed by the ethyl, followed by the methyl. So we go clockwise or to the right. So would this be R?
No, S. It's S.
Be S. Why?
The lowest priority is S.
Yeah, the lowest priority is a wedge. So this would be an S stereocenter. All right. The cheesy view I like to do is this, where I have H and T, and then I've got 2 crossbars through them. And then I have F, 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 F. This is my cat tummy view. It's a little bit cheesy, right? So H is the head, T is the tail. Your cat's on its back with all 4 feet pointed out towards you. So if you're going to draw this one out, it would look a little bit weird. But you'd have this foot as a wedge. It's not a fluorine, it's a foot. This fluorine as a wedge. That fluorine as a wedge. Your head would be a dash. And your tail would be a dash, right? So imagine a cat laying on its back. That's essentially what the Fisher's view is going to do. That definitely made it stick in my head when I was learning it. You guys want to try one more example or dive straight into problem solving? I'll put one example on here. For those of you that want to do the problem solving, you can get started on the activity, and then I'll do this one on the board. Let's say I've got this compound, got a hydrogen over here, OH, H, and OH. We've got a red stereocenter up here, and then a green one down here. Let's assign stereochemistry to each of them. So red one first, what would the highest priority be? Bromine. Followed by what? Oxygen. Followed by what? Carbon down here. Okay, so I'm going to the left, but that hydrogen is what? Coming out towards us, so what should this be? R. All right, let's do the same thing with green. What would be the highest priority for that green substituent? Chlorine. Followed by this methyl, or that carbon right there. So we'd be going counterclockwise to the left again. So what would that be? R. So this is pretty handy. It saves you a lot of hassle when it comes to drawing dashes and wedges, and you usually see it with carbohydrate chemistry. You don't see it as often with other chiral molecules. Make sense? All right, so with the small group activity, you're welcome to push tables together, move around, but I do want you guys to try to work through as many problems as possible with the remaining time.